So let's look at an example of finding the complex Fourier coefficients for this waveform here. We have this sawtooth waveform. Apparently, this waveform has the period of fundamental period of 0.1 second, and the omega therefore is going to be equal to 2 pi over t. That's 20 pi reading per second. And we're gonna find c for n is equal to 0, so cn is c0, and just equal 1 over t, and it goes from 0 to t ft times e to j minus j n z and n equal to 0 and omega t, right, dt. So therefore, this is the same as the average we'll find. So we have 1 over 0.1 times 0 to 0.1 times ft. Ft during this interval, when t greater than 0, less than 0.1, the t is just equal the ramp function. That's 2 times t over the period, so that's t over 10, that's 20 times t, right? So this is a ramp function. So when t equal to 0.1, ft equal to 2. And we're gonna substitute this 20t dt, and you can integrate this by using mathematically, and the t integrate t, you gotta have a t squared, right? So we can get that. So we got 20 over 2, that's 20 over 0.1, I'm sorry, 0.1 times half of t squared. We evaluate that at t equal to 0 to 0.1. So we get that's equal half, that's equal 20 over 0.1 times half times 0.1 square, and this 0.1 be cancelled, right? So actually this is equal to 1, right? So that's the, also if you look at the waveform itself, if you try to find the area underneath this, therefore you get a half times 0.1 times 2, and that's the area. Then you divide this by 0.1, so therefore you got a 1 there. You don't so this is another way of kind of checking this c0. Let's see cn. Cn is more interesting. Cn is equal to 1 over t, 1 over 0.1, 0 to t, which is 0 to 0.1. ft is 20t, right? e2 minus j n omega t, n times omega is 20 pi, right? 20 pi t dt. And this integration here is very interesting. So what we have here is based on the fact that is the e2at dt is going to be equal 1 over a times deat. And therefore, based on that, we got a cn is going to be equal, let me try write this 20 over, so I move this 20 out, so 20 times 0.1 over 0.1, I integrate from 0 to 0.1, I have a t times 1 over a, so all the things in front of t in the exponent of this exponential function there, that's negative j 20 n pi, right, times e2, now the e2, now d e2 minus j 20 n pi t, right? And also based on the fact of the chain rule, we have x dy is going to be equal dxy minus y dx, something like that. And if you recognize, so this is a constant, we're going to move this out, and let's call this as x, and this is the y. So therefore we're gonna do cn is, we move that constant out, so we have 20, yeah, so let's cancel this 20. Yeah, let's keep that 20. So we don't really combine too many steps. So multiply 1 over negative j 20 n pi. So now we cancel this 20, and then the integration, we have a dxy, so that's just x times y. We evaluate that at, so that's multiply the xy, x is t times y is e2 minus j 20 n pi t. Right, we evaluate that the t at equals 0 and 0.1. So that lower limit t, because we have a t here, that's the term 0. And then we have the other term, which is minus y dx. And that one we have a 0 to 0.1. Y is e2 minus j 20 n pi t. And y and the x dx is dt. And we know this term is 0. The reason for that is because you integrate a complex number. The real part is cosine function and the imaginary part is sine function. So therefore you end up with integrate two sinusoidals. So therefore this one is 0. And we're going to need to evaluate the first one only. And therefore we have what's we left here. So we have 1 over negative j 0.1 n pi. And the inside this we have 0.1. So t we replace t by 0.1 times e2 minus j 20 times 0.1, no, 20 n pi 0.1, and minus 0, right? Because this one is 0, so I'm not gonna count that term anymore. So we have 0.1 be cancelled. And this term actually is equal e to negative j 2 n pi. And remember, this is equal cosine negative 2 n pi and plus j times sine negative 2 n pi. This is just the Euler identity, right? So this would be equal to 0. This would be equal to 1, right? Because the cosine n pi any is equal to cosine 0, that's equal to 1. And so therefore the final number is very compact. It's going to be equal negative 1 over j n pi. Or we can see this is equal, because 1 over j is equal negative j, right? So we actually have j times 1 over n pi. So this is really compact form, right? So this is the Fourier coefficient, is a complex one. And let's look at whether this works. And I also had a Python code here. And I basically utilize the Fourier coefficient we just calculated. And similar to what we had before, I defined the original function, the sawtooth waveform, and also define the Fourier coefficient, the complex one. So the Cn, as when n is equal to 0, I get to 1, because we calculate that's equal to 1. So when n is not equal to 0, we have 1 over equal j over n pi. So I'm using the complex Fourier coefficient. Now I'm reconstructing the waveform using the complex Fourier coefficients. So I'm adding all these components. Now I need to add from a negative n to positive n, right? And if you look at the Cn and the C negative n, they are conjugate to each other. And also e2 j n omega t and e2 minus j n omega t, they're also conjugated to each other. So therefore, what I did was is Cn or Ck times the e2 j n omega t or k omega t, and I take the real parts and multiply by 2, because the c times the e2, the exponential function, these are the conjugate to the ones with the negative n, right? So I did this and see whether we can approximate this waveform. Right now I have n equal to 10, which in this one here, let's see if I have if I change this number, and this is how close we are approximating this original waveform, original sawtooth, right? We have that goes from 0 to 2, and if you want to find the detail how I plot this, I'm basically using the tangent, arctangent stuff to get this function plotted. And let's see if I change this to 50. Right now I have 22,000 points. So let's see, we change it to 50. So 50. I don't. Yeah. So this is the with the 50 Fourier coefficients. Right. If let's see, if we do 200, that should getting even closer as we're getting for the waveform, for the reconstructed waveform. So we get a better match. Now you see this, the orange reconstructed waveform is very close to the original, the sawtooth waveform, right? We know our Fourier coefficients, the calculation is correct. Okay, so that's the example for the complex Fourier coefficients. And I hope you enjoyed the lecture. And remember, no matter what you do, just keep going, never stop. Okay, I'll see you next lecture.